Welcome all. So let us continue our lecture. We are still in chapter 6, 6.2. And we're still talking about sets. Let us review what we learned so far. Then we're going to start this new content. Recall that we said set theory is a very important and fundamental concept for structured query language and database systems. Set theory. The elements of set theory are sets. The elements of set theory are sets. Well, recall what a set is. Set is a collection of objects. Okay, remember that when we're talking about sets, we use capital letters like S, A, and so on, and we represent the set using curly brackets. For example, set B is the set including some objects like 1, 2, 3, and so on. There you go. We said that, okay, now that we've defined these objects, we're interested in combining them together and represent some new objects. Okay, we defined operations between sets. Remember that the very first operation that we talked about was doing the complement of a set. To have the complement of a set, we need to define a very big set that we call the universal set. So to define set complement, we use a very huge set that we call universal set. In a sense, we try to give a framework to the collection of all sets. And remember, we usually represent the universal set by a rectangular shape, and we just denote this guy by U. Inside the U, we have a lot of different sets. The complement of a set like A, remember that it's denoted by a little c on top of it, a complement. And note that if you open different discrete math books, you might see prime or bar. The meaning of those is the same as the complement of a set. Okay, a bar and a prime. This new set says, hey, we are taking all of the elements that are not in set A. They belong to the complement of set A. So we represent this by the collection, the set of all X values that are in universal set, or sometimes we just don't denote this, such that with the condition that X is not a member of A. Not a member. Remember that we just use logic to connect this new concept with what we learned before, which was the negation. So equivalently, we have negation. They are equivalent to each other. Then we talked about the intersection between two sets. A intersection B, which includes all the common elements between A and B, the set of all x values such that x belongs to A, and at the same time, the connector between them is and x belongs to B. Remember that, getting back to what we learned at the beginning of the course, we are talking about and. So intersection and the wedge operator, they are connected together. The next one is the union between two sets. A union B is the set of all x values such that that element is either in the first set or in the second set. It might be in the common area between these two as well. X belongs to A or X belongs to B. So union is connected to or. Well, we talked about the difference between two sets as well. A minus B includes all the elements that are in the first set, but not in the second set. We are subtracting all the elements that belong to B from A. So this is the set of all elements like X such that X is in A and X is not in B. This is what we learned before. Very well. We also talked about mutually disjoint sets. We said two sets are disjoint from each other if they have no intersection. Two sets like A and B are called mutually disjoint or just disjoint if and only if their intersection is empty. There is no element that belongs to A and belongs to B. They're separated from each other. Like this case, you have set A and set B. Very well. If we have a collection of sets, instead of just listing them as A, B, C, D, we use indices to represent those sets. Definition. Sets like A sub 1, A sub 1, A sub 2, A sub 3, and so on, are mutually disjoint or pairwise disjoint if and only if you're taking these sets 2 by 2, pair by pair, and there is no intersection between them. If and only if A sub I intersection with A sub J is empty. note that we are separating these sets from each other. So I and J are not equal to each other. It means that we are just taking those sets that are different from each other. Of course, if you take A1 and A1, A1 and A1, the intersection is equal to A1. So it's very important that we take sets that are different from each other. If the intersection of those sets are all empty, we say that, hey, we have a collection of sets that are mutually disjoint from each other. So now it helps us to define a partition for a set. Remember, we talked about quotient remainder theorem. We talked, hey, based on the division by 2, based on the division by 3, division by 4, division by 5, and so on, we get different remainders. Using different remainders, we can divide up Z into some portions, or we can define partitions. So definition. Definition of partition. For a partition, we need a large set. Think about set Z. So suppose A is a set. Then a collection of non-empty sets, non-empty sets. So note that we already put this condition that these sets are not empty. A collection of non-empty sets like A1, A2, A3, and so on. Since we are working with a collection of sets, let us put them in set notation. Is called a partition for A if and only if satisfies these two conditions. First of all, AI intersection AJ is empty. It means that they are mutually disjoint. And 2, the union of A1, A2, A3, and the rest of them is equal to A itself. So again, definition of a partition. Suppose A is a set. We have a set. A collection of non-empty sets. A sub 1, A sub 2, the rest of them is called a partition for this large set A if and only if we have these two conditions. First of all, they are mutually disjoint. Second of all, their union is equal to set A itself. So how do we visualize that? Give us an example. So suppose you have a large set, like set A. You're dividing this set into smaller sets that have no intersection. So suppose this is set A1, set A2, set A3, A4, and the rest of them. There is no intersection between these sets, and their union is equal to set A. Well, so give us an example from what we saw before. Okay, think about Z. Example that we saw before. Consider Z, the set of all integers, and think about quotient remainder theorem. Quotient remainder theorem. Okay, remember that if you have a number n and you divide that by, for example, 2, you can find two unique numbers, q and r, such that r is bounded between 0 and 2. If we divide any number by 2, the remainder is either 0 or it is equal to 1. So n is either 2q or n is equal to 2q plus 1. From quotient remainder theorem, we have this result. So what's the meaning of that? It means that we have even numbers, odd numbers. Even and odd numbers. What's the meaning of that? It means that we can divide up Z into two sets, the set of even numbers, the set of odd numbers. So this is your Z. We have a partition for Z. This partition says, hey, you have even numbers and odd numbers, set A sub 1 and set A sub 2. You can verify these conditions. They are non-empty, of course. Even numbers, 2, 0, -2, odd numbers, 1, -1, 3, -3, and so on. Non-empty. The intersection is equal to empty. Of course it is. There is no intersection between A1 and A2. The set of evens and odds, they have no intersection. We don't have a number that is even and odd at the same time. And if you take the union of these two sets, is equal to A2 is equal to Z. All conditions are met. We just represent a partition for Z. Now you might say, well, what if I divide by 3? Can I represent a new partition? Dividing by 4, 5, 6? Of course. Dividing by different numbers give you different partitions for set Z. So what if I divide by 3? How do I represent that partition? Dividing by 3 gives you 3 subsets, a new partition. So let me write this guy here. N is equal to 2q, n equals to 2q plus 1. Now dividing by 3 gives us a new partition. What is that partition? Well, n equals to 3q, or n is 3q plus 1, or n is equal to 3q plus 2. Okay, well, let's see what we have. This is Z. I'm going to represent a new partition for Z. I'm going to define set A sub 1, A sub 2, A sub 3. And I'm going to claim that these three sets, they have no intersection to each other. A1, intersection A2, intersection A3. So let us write this as pairwise disjoint. A1, intersection A3, and A2, intersection A3 is empty. So they are pairwise, or they can say that mutually disjoint, and A1 union A2 union A3 is equal to Z. The collection of numbers, multiples of 3. The collection of numbers that we divide them by 3, the remainder is 1. And the collection of numbers, when we divide them by 3, the remainder is equal to 2. We just represent a new partition, so new partition for Z. These two partitions are different from each other. Well, what is a power set? Power set is the collection of all subsets of any set. So a power set. Definition of power set. Suppose you have a set like A. If you list all of the possible subsets of that set and put them inside a curly bracket, we call it power set. Let A be a set, and suppose the cardinality of set A, or the size of set A, is equal to n, and n of A is equal to n. So the size of set A is n. Okay. Power set of A denoted by P of A is the collection of all subsets of A, and the cardinality of power set is 2 raised to n. So n of P of A is equal to 2 raised to n. The size of, this is the size of power set of A. For example, suppose you have this set. Suppose you have a set with cardinality 2. Example. Let A be a set including X and Y. Okay. What is the power set of A? What is P of A? What are the subsets of this set? Okay, remember that we said empty set is the subset of any set. And the size of empty set is equal to 0. So empty set is a subset. So empty set is a subset of A. So empty set belongs to power set of A. Well, I'm going to take one element at a time and construct subsets. Set including just one element is a subset of A. So set including X belongs to power set of A. Let me just put these in circles so we know what are the elements of power set of A. Set including Y is a subset of A. We already know that. So set including Y belongs to power set of A. This is the third element in power set of A. What about the set A itself? Well, set including X and Y, which is equal to A, is a subset of A as well. What's the meaning of that? It means that the set including X and Y is a member of power set of A. Okay, as you can see, we found all members of power set of A. Power set of A includes empty set, set including X, set including Y, and set including X and Y. So it has 4 members. The cardinality of P of A is 2 raised to 2, which is 4. So let me write this right down here for you. The cardinality of P of A is equal to 2 squared or 4. Very well. So in 6.2, we start talking about methods of proofs for sets. Exactly the same as what we did for logic, we have some rules, some basic rules that all of them can be proved by direct definition, connecting them to the definition of intersection, union, negation, which is related to set complements, and logic itself. So on page 1, we're talking about theorems. Page 1. Theorems. So here we have sets. Let A, B, C are sets. So we have a collection of objects, collection of numbers, whatever they are. The first one is called inclusion of intersection. Inclusion of intersection. So what does this guy tells us? It tells us A intersection B is a subset of A, and also it is a subset of B. So it says, hey, if you have 2 sets, like A and B, if you take their intersection, that intersection is a subset of the first set and also a subset of the second set. Okay, visually it makes sense. Okay, when we look at this, we say, this is the intersection between them. I can see A intersection B is a subset of set A, and A intersection B is a subset of set B. Visually, we can easily verify that. But how do we prove that mathematically? If somebody says, okay, you know, some theorems in set theory, how do you prove it? So, prove by definition. Let us try our best to use the definition, direct proof, and show that A intersection B is a subset of A. So this is our goal. Our goal is to show that A intersection B is a subset of set A. This is our goal. That's what we're trying to prove. Recall that. We want to show that a set is a subset of another set. What we have to do, we have to show that a random element in this set is included in the larger set. So we need to show that any element in A intersection B belongs to A. Belongs to A. So this is what we're trying to show. Let us take a random element in set A intersection B. Let X be in A intersection B. What are we trying to show? We're trying to show that X is in A as well. I'm going to put a question mark here because I want to prove this. I don't know if it is true or not. This is my goal. I want to show that the random element lands in set A. Well, what is the definition of the intersection? We know that A intersection B is the collection of all elements like X such that X is in the first set and X belongs to the second set. Since X is in A intersection B, this is our assumption. Since we know that, using the definition, by definition, X belongs to A, X belongs to B. By definition, X is in A, which results in what we try to prove. We're done with our proof. By the same argument, we can show that that element lands in B as well, and you're done with the proof. The second one is inclusion in union. Inclusion in union. It means that A is a subset of A union B, and B is a subset of A union B. Well, let's take a look at the Venn diagram. We have set A, we have set B. Remember, the union includes every element, either in the first set or in the second set or in the intersection. So we shape everything when we're referring to the union. This is A, union B. Okay, where is A? A is a set here, which, as you can see, is a subset of this pink set, which is A, union B. Let's go here. We're going to look at set B. Well, set B is just right here. Set B is this small set, part of this shaded pink A union B. So visually you can see that this set B is a subset of this set also for A. But mathematically, how do we prove that? Mathematically, the proof, our goal is to show that if I take any random element in A, that random element belongs to A union with any other set. I don't care what that set is. A union with any other set. So our goal is to show that any random element in A is in A union B. So let us use the method of direct proof definition. Okay, definition. Let X belongs to A. Since X belongs to A, since X is in A, X is in any set union with A. Any set union with A. It doesn't matter what that set is. So X belongs to A, union with any set. Again, I don't care what that set is, any other set. So X belongs to A, union with any set, that set can be B. A, union B. So this was our goal, to prove that X belongs to A, union B, which we just proved. The proof is very straightforward. X belongs to A, it belongs to A union with any other set. On page 3, we have important set identities. As you remember, we had the exact same thing when we talked about logical operators. Let all sets referred to below be subsets of a universal set like U. The very first law is commutative law. For all sets like A and B, A union B is the same as B union A. It means that you can just switch them. Like P or Q is the same as Q or P. Also, we have the exact same thing for intersection. A intersection with B is the same as B intersection with A. P and Q is the same as Q and P. Associative laws for all sets, A and B and C. It doesn't matter if you group A and B, then C, the result is the same as grouping B and C together using union, then take the union of that result with A. We have the same process for intersection. The intersection between A and B, then C, is the same as taking the intersection between B and C first, then we take the intersection with A. The result is going to be the same. 3. Distributive laws. Well, as you remember, in logic, we can distribute or over and. Also, we can distribute and over or. We have the same thing for union over intersection. We can distribute union over the intersection between two sets. A union with B and C is A union with B intersection with A union with C. So remember that you have equality in between these two. It means that if it's written in expanded form, like A union B intersection A union C, you can write this in compact form. From left to right, we can use the distribution. From right to left, we can write it in compact form. Again, the same for intersection over union. A intersection with B union C is the same as finding the intersection between A and B, finding the intersection between A and C, then take their union. Identity laws. The union of A with empty set is always A. The intersection between A and the universal set gives you set A itself. The complement laws. If you take the union between A and its complement, the result is the same as universal set. However, there is no intersection between set A and its complement. A intersection with its complement is always empty. They are mutually disjoint. Double negation and double complement law. The complement of a set is the same as the set itself. So double negation of a statement is the same as that original statement. You have the same thing for set theory, double complement. Idempotent laws. The union between A and A is A. The intersection between A and A is A. Well, universal bound laws. Union between A and the universal set gives you the universal set. The intersection between empty set and any set is always empty. We also have the Morgons laws, as we had for logic and propositions. Here, the complement of the union of two sets is the intersection of their complements, and the complement of the intersection between two sets is the union of their complements. Well, absorption laws. A union with A intersection with any set, it doesn't matter what that set is always A. If you find the intersection between A and A union with any set, the result is A itself. Well, the complements of the universal set and the empty set. What complement the universal set is actually the empty set, and the complement of empty set is the universal set. And finally, one important law helps you to rewrite the difference between two sets into intersection. So if we have A minus B, equivalently, you can write it as A intersection with B complement. There we go. So give us some proofs. Well, I'm going to prove these two for you. The very first one, I'm going to prove one of the distributive laws for you, and the other one, I'm going to prove the Morgons laws for you. How do we use the direct definition and the logic to prove this? Well, on page 4, we're going to prove for all sets, like A, comma B, comma C, we have the following. A union with B intersection C is equal to A union B intersection A union C. Okay, proof. We want to show that two sets are equal to each other. Note that. Let me write this note for you to show two sets. Like X and Y are equal to each other. So to show that X is equal to Y, we need to show that X is a subset of Y and Y is a subset of X. If and only if X is a subset of Y and Y is a subset of X. Not for you. Okay. So suppose this is set X and this is set Y. We want to show that these two sets are equal to each other. So we want to show that X is a subset of Y. Then we jump around, we show that Y is a subset of X. So proof. Let us use the definition of direct proof to prove that X is a subset of Y. You show that X is a subset of Y. To show that X is a subset of Y, we need to show that any random element in X lands in Y. So we need to show that for any random element like X in set X, that element lands in Y. Let us put a question mark here. This is our goal. We haven't proven it yet, so that's why we put a question mark on top of the conclusion. Well, okay. X is in here. X belongs to X. What is X? It means that X belongs to A union B intersection C. Well, what is the definition of union? What is the definition of intersection? So we have to play around with this. By the definition, of union, what do we have? We have X belongs to A or X belongs to B union C. So this is the definition of union. And then, so definition of the union, X belongs to A, or X belongs to B union C. I'm sorry, B intersection C. Or I wrote union, I don't know. Here we go, the intersection. Okay. X belongs to A. X belongs to A. And don't forget that you're trying to show X belongs to this intersection. This is our goal. So remember that X belongs to A. What's the meaning of that? It means that X belongs to A union with any set. Any set. It doesn't matter what that set is. That set can be B. X belongs to A. It means that X belongs to A union with any set like C. So X belongs to A union C. So what's the meaning of that? X is in A union B and X is in A union C. So X belongs to A union B intersection A union C. Well, what if X belongs to B intersection C? The definition of intersection by definition of intersection. Definition of intersection, X belongs to B and X belongs to C. Again, X belongs to B. What's the meaning of that? It means that X belongs to B union with any other set. So X belongs to B union with any other set, like A. X belongs to C. It means that X belongs to C union with any other set, like A. So what's the meaning of these two? It means that X belongs to B union A intersection C union A. But commutative law says you can switch in between these two, A union B and A union C. So in these two cases, we just showed that X belongs to Y. So this guy resolve this guy resolved in this. Well, so we showed that X is a subset of Y. Now we want to show that Y is a subset of X. Proof. Let's continue this. We just showed that X is a subset of Y. Now we show that Y is a subset of X. What's the meaning of that? It means that we have to take a random element like X in Y and show that that element lands in X. So let X be in Y. It means that X belongs to A union B intersection A union C. Okay. By the definition of intersection. Definition of intersection. X belongs to A union B and X belongs to A union C. X is in the first set and X is in the second set. Okay, so what's the meaning of this guy? By the definition of union, X is in A or X is in B. By the definition of union, X is in A or X is in C. Well, what do we have here? We have X is in B, X is in C. The connector in between them is AND. So X is in B and X is in C. It means that X is in B intersection C by the definition of intersection. And at the same time, X is in A or in that intersection. So what do we have? X belongs to A union B intersection C, all using the direct definition. So we just showed that X belongs to X. So we just showed that Y is a subset of X as well. Here we have X is a subset of Y, Y is a subset of X, so X is equal to Y. This is what we try to prove. Well, another interesting theorem is the Morgons Laws. So we're going to prove one of them here. So we are on page 5. Let A and B be two sets, then A union B complement is A complement intersection B complement. Again, remember that in logic we had the negation of P or Q equals to not P and not Q. So the complement acts like negation. And also recall that when we talked about complement of set A is the set of all elements that X is not in A. It's not the case that X is in A. It is not the case that X belongs to A. Okay, let us start the proof. You have X, you have Y. You need to show that X is a subset of Y and Y is a subset of X. This is our X and this is our Y. So let us show that. Let us show that X is a subset of Y. It means that any random element in X belongs to Y. So let X belongs to X or X belongs to A union B complement. Our goal is to show that X belongs to A complement intersection B complement. So let me just separate these. Okay. Direct definition. The definition of complement. So what does it tell us? It tells us X belongs to A union B. What's the meaning of that? It means that X is not a member of A union B. It means that X is not a member A union B. X is not a member of a set. It is not the case that X belongs to that set. It is not the case that X belongs to A union B. But what was the union? X is in A or X is in B. From set theory, we're moving to logic. It's not the case that X is in A or X is in B. Logic interpretation, it is not the case that negation X is in A or X is in B. So logical interpretation, it means that we distribute the negation over. We have X is not in A and X is not in B. What's the meaning of that? It means that X is in A complement and X is in B complement. X belongs to A complement and B complement. Okay, so we just showed that X is a subset of Y. Now we show that Y is a subset of X. So we just proved that X is a subset of Y. Now we show that Y is a subset of X. It means that we need to take a random element in Y and show that that random element belongs to X. Let X belongs to set Y or X belongs to A complement intersection B complement. Our goal is to show that X belongs to X or A union B complement. Okay, let us start. X belongs to the intersection by definition of intersection. X belongs to A complement and X belongs to B complement. Well, okay, what do we have here? It means that X is not a member of A. It's not the case that X belongs to A. It is false that X is in A and it is false that X is in B, or it's not the case that. Well, okay. So remember that it is false, it's not the case, is the negation. So what are we trying to do? We are trying to somehow factor out it's not the case or it is false. So it is false that X is in A or X is in B. It is false, it's not the case, gives us the complement. So equivalently, we have A or B complement. So we just showed that X belongs to the complement of the union of two sets. 1 and 2, X is a subset of Y, and Y is a subset of set X, results in X is equal to Y. We just prove this law.